On average, about 90% of all species an organic chemist comes across are common neutral species, such as tetrahedral carbons, bent oxygens, and trigonal pyrimidal nitrogens, in addition to cations and anions. However, there are a few more esoteric species, and these include radicals and enes, such as carbenes and nitrenes. We will consider these starting with radicals. Carbon radicals come about with a common tetrahedral carbon's loss of an electron associated with an R group. The carbon has 4 valence electrons, and here 4 electrons associated with carbon from 6 divided by 2 equals 3 electrons from covalent bonds and 1 electron radical. Thus, 4 minus 4 shows us 0, so the radical is neutral. There are a total of 7 electrons in the outer shell of the carbon, 4 associated with carbon and 3 electrons with R groups, and shared with carbon through covalent bonds. This is not hypovalent, as there are not an even number of electrons less than 8. Like the carbocation's positive charge, the single electron of the radical species is found in a p orbital, and where the carbon is attached to 3 R groups through 3 single bonds, the structure is trigonal planar where the R groups are H. But if the R groups are changed to start with a carbon, the structure alters from planar to slightly pyramidal shape. The oxyl radical is generated from the common oxygen species with the loss of an electron associated with an R group. There are 6 valence electrons, and in this case, 6 electrons associated with the oxygen from 2 divided by 2 equals 1 electron from covalent bonds and 4 electrons from lone pairs, as well as 1 electron radical. Thus, considering 6 minus 6 equals 0, this oxyl radical is a neutral species. In total, there are 7 electrons in the oxygen's outer shell, with 6 electrons associated with the oxygen and 1 electron associated with an R group and shared with oxygen through covalent bonds. A great example of this is the molecule called 2266 tetramethyl piperidine 1-yl oxy, abbreviated to TEMPO. The oxygen radical is stabilized by the nitrogen atom's lone pair of electrons and the methyl groups that hinder the approach of other molecules to the oxygen radical. It's used for the oxidation of alcohols and to stop radical polymerization processes. The nitrogen radical is called an aminyl radical. A common trigonal pyrimidal nitrogen would lose an electron associated with an R group to become an aminyl radical. Nitrogen has 5 valence electrons, and this aminyl radical has 5 electrons associated with nitrogen, due to 4 divided by 2 equals 2 electrons from covalent bonds, 2 electrons from a lone pair, and 1 electron from the radical. Thus, 5 minus 5 equals 0, to tell us that this species is also neutral. In total, there are 7 electrons in the outer shell of this nitrogen, with 5 electrons associated with nitrogen and 2 electrons associated with R groups that share through covalent bonds with nitrogen. Now, there is another aminyl radical species. Starting with neutral trigonal pyrimidal nitrogen, we can lose an electron from the nitrogen's lone pair. It is very common that radicals are neutral in terms of charge. However, if we consider this species with nitrogen's 5 valence electrons and this aminyl radical having 4 electrons associated with this nitrogen, with 6 divided by 2 equals 3 electrons coming from covalent bonds and 1 electron from the radical. Now, considering the calculation of valence electrons minus associated electrons, that here is 5 minus 4 equaling plus 1. Unusually for a radical, this is a positive charge. In total, there are 7 electrons in the nitrogen's outer shell, 4 electrons associated with the nitrogen, and 3 associated with the R group and shared through covalent bonds. With enes, we will start by looking at the carbon species called a carbene. If we take our common tetrahedral neutral carbon and remove 2 electrons associated with R groups, we will arrive at the carbene species. Considering carbon's 4 valence electrons and 4 divided by 2 equals 2 electrons from covalent bonds and 2 electrons from lone pairs or radicals, don't worry, we'll explain that in a minute, we will see that 4 minus 4 equals 0 to tell us that the carbene is neutral. Total electrons in this carbon's outer shell is 6, with 4 associated to carbon and 2 associated with R group and shared through the covalent bond, and thus it's hypovalent. The carbene is commonly an sp2 center, but there are 2 possible forms. The first has 2 unpaired electrons, and they both have the same spin state. They are degenerate, that's to say, the same energy. One of the non-bonding electrons is in a p orbital, and the other non-bonding electron is in an sp2 orbital. And the angle between the R groups is of between about 100 to 110 degrees. The 2 unpaired electrons give a multiplicity of 3, calculated by the number of unpaired electrons plus 1. So 2 plus 1 equals 3. Hence, it's described as the triplet state. Their behavior has similarities with diradicals. The other form has 2 non-bonded electrons paired together and are found in the sp2 orbital with an empty p orbital. The angle between the R groups is about 130 to 150 degrees, showing a clear spatial difference with the triplet. As the electrons are paired, they have opposite spins. Here, there are no unpaired electrons, thus a multiplicity of 0 plus 1 equals 1, so a singlet state. There is a small energy difference between the 2 states of 32 to 42 kilojoules per mole for methylene, where the R is H. The nitrogen equivalent is called the nitrene. The common trigonal pyrimidal nitrogen will remove 2 electrons associated with R groups to provide a nitrene. Considering nitrogen's 5 valence electrons and the electrons associated with this particular nitrogen having 2 divided by 2 equaling 1 electron from covalent bonds and 4 electrons from lone pairs or radicals, 5 minus 5 equals 0, to tell us that the nitrene is neutral. It has a total of 6 electrons in the outer shell, 5 associated with nitrogen and one associated with an R group that's shared through a covalent bond. So the species is hypovalent. Again, there are two forms of nitrene. However, it can be challenging to determine their structure. One has a lone pair, but critically two unpaired electrons, both with the same spin state, one in an sp2 orbital with the other in a p orbital. This is the triplet state. The other form has two lone pairs in sp2 orbitals, and the p orbital is empty. This is the singlet state. There is a much larger difference in energy between singlet and triplet state for nitrene of 145 kilojoules per mole, where R equals H, than was the case with the carbene.